So let's start the second half of the lecture doing a mass-to-mass style problem. Okay, so the example is ethanol with a molar mass of 46.1 grams per mole is synthesized by reacting ethylene, C2H4, with a molar mass of 28.1 grams per mole with water. How many grams of ethanol are formed from 14 grams of ethylene? So the first thing we should do in any of our problems is take a look at the balanced chemical equation, or at least look at the chemical equation and make sure it's balanced. Is this balanced? Well, I've got 2 carbons on each side, 6 hydrogens, and an oxygen on each side. So this is indeed balanced. But I never ever trust anybody to balance my equations. I always double check, because I've seen so many times where in a homework problem, the student does so many things right, but the balanced equation is wrong. And if the balanced equation is wrong, you can't get the correct answer. All right, so what we're going to do is we're going to start off with our mass of our reactant, and we're going to convert that to moles of the reactant. Okay, and we use molar mass as a conversion factor. Remember that little island picture we drew? To go from mass island to mole island, we divide by the molar mass. Then, to go from moles of reactant to moles of product, we use that mole-to-mole conversion factor. This comes from the balanced equation. Then moles of product to grams of product using the molar mass conversion factor. So, I'm going to start with what I've got, the 14 grams of ethylene, and I'm going to turn that into moles by dividing by the molar mass. That means the grams of the ethylene cancels. Then, for every 1 mole of ethylene used, I make 1 mole of ethanol. So, my conversion factor is a 1-to-1 conversion factor. Then I convert back to mass using the molar mass of ethanol. And when I do that, I get 23 grams of ethanol as a product. This type of problem, mass to moles to moles to mass, is very, very common. Okay, it's something you should become very proficient with doing. Grams to moles, moles to moles, moles to grams. Okay, so practice these types of problems. All right, so that problem we just did said if I have 14 grams of ethylene, I'm going to make 23 grams of ethanol. That is what we would call the theoretical yield. This is what we would get if theory holds up and all of our ethylene gets converted into ethanol. Okay? However, that is often not the case. There's lots of different things that could happen. I could lose some of my product due to overheating or evaporation. I could not get a 100% reaction. Some reactions only go just a few percent to completion. So what we actually get is the actual yield. This is the amount of product that we get from the reaction. So theoretical yield is the calculated amount, and actual yield is the experimental amount. So when a chemist does a reaction, we often like to talk about our efficiency. This is what we would call a percent yield. The percent yield is simply how much we make, our actual yield, over how much we should have made, our theoretical yield. So in our example problem here, if the reaction of ethylene with water to form ethanol has a calculated theoretical yield of 23 grams, that's what we just calculated in that previous problem. What is the percent yield if only 15 grams of ethanol are actually formed? So that is our actual yield. So if I take my actual yield over my theoretical yield, I see that I'm only 65% successful for this reaction. Now the problems we've done up to this point have assumed that we've had plenty of water to react with our ethylene, okay? In other words, we're only looking at what if I used up one of my reactants. So that's not always the case. So that's what a limiting reactant style problem is for. Limiting reactant is the reactant that gets completely used up in a reaction. Okay? So, an example would be if I want to make sandwiches. If I want to make sandwiches, I know my recipe for sandwiches is 2 slices of bread plus 1 slice of meat equals 1 sandwich. Okay? So how many sandwiches can I make if I've got 1, 2, 3, 4, 5, 6, 7, 8 slices of bread? So 8 bread, 3 slices of meat, how many of my product can I actually make? Well, I can only make 3 sandwiches because my meat gets used up first. That is what we would call the limiting reactant. It is the substance that is used up first in a reaction. The bread would have leftovers. Okay, that is what we would call the excess reactant. Okay, the reactant in excess. Now, to do a limiting reactant problem is actually really simple. It is exactly the same style of problem as we did with the ethylene example. You just have to do it multiple times. Now, your book takes this crazy way of determining a limiting reactant. It works. If you want to go this way, I'll let you, but this is not something I would teach, okay? So, we continue through this. Not going to teach this portion. Not going to teach this. Not going to teach this, okay? And the reason is, you already know how to do the normal mass-to-mass style problem. Why not just do it twice? So, let's actually do the problem the way that I would actually do the problem. So, using the balanced equation, determining the limiting reactant when 10 grams of N2, and they give us the molar mass, react with 10 grams of O2, and they give us the molar mass. Okay? In other words, I've got 10.0 grams of this and 10.0 grams of this. So what I do is I see, okay, how much can I make of this if the nitrogen is used up? Okay? And the way I do that is I just take my 10 grams of nitrogen times 1 mole of nitrogen is 28.02 grams of nitrogen times my mole ratio. For every 1 mole of N2 that goes on the bottom, because I need to cancel it out, I make 2 moles of NO. Okay? Now, I'm going to tell you something. This problem is asking us to determine the limiting reactant, which is fine. I actually could stop here, because whoever gives me the bigger number of moles of my product is going to be the reactant that's in excess. Whoever gives me the least amount of moles of product is going to be my limiting reactant. But I'm going to tell you, most problems don't stop with that sort of information being asked for. Most problems, most real-life problems, would have you converting to grams. Okay? So what I would do, and again, this is me, because a lot of questions would ask, well, how much nitrogen monoxide would you make? Well, so what I would do is I would convert the moles of nitrogen monoxide to grams of nitrogen monoxide. So 1 mole of NO is, let's see, 14 plus 16 be 30.01 grams of NO. Okay? So that's the setup. I don't have a calculator handy, so that's how we set this problem up. I'm going to do the same thing, but if O2 is used up. So in this case, I would take the 10.0 grams of O2 times 1 mole of O2 is the 32.00 grams of O2 times, I still make 2 moles of NO for every 1 mole of O2. And again, I would carry that through to grams. 30.01 grams of NO is 1 mole of NO. Okay? Now, I don't have a calculator present, so give me one moment and I will come back with these values all calculated. And ta-da, magically I have my answers. And we see that the nitrogen would give us 21.4 grams of nitrogen monoxide, but oxygen would only give us the 18.8 grams of nitrogen monoxide, which means oxygen is used up. This is my limiting reactant. Now, this would be my theoretical yield for this reaction. Okay? So your limiting reactant is used to calculate your theoretical yield. So that's one of the reasons that I just carry through my calculation all the way to the mass stage, because a lot of times I'm going to want that theoretical yield. All right, the last thing in the chapter is oxidation and reduction. And we talked about this in the lab. Oxidation is the loss of electrons. Oxidation is loss. Reduction is the gain of electrons. Now in the lab I told you, lose electrons, Leo the lion goes, grr, gain electrons, reduction. Another way to remember this is just oil rig. Oxidation is loss, reduction is gain. Okay? Now both of these processes have to occur simultaneously, because you can't lose an electron without it going somewhere. Okay? Whoever loses something somebody else has to gain something. Okay? So we call this a redox process when a reaction involves a transfer of electrons from one substance to another. So, as we saw in the lab, if I put zinc with copper ions, I plated out copper onto my zinc pieces, and zinc ions go into solution. So zinc went from having a full complement of electrons to now missing 2 electrons. So that means this was oxidized by 2 electrons. Copper went from having a 2+ charge to not having a charge at all, gaining its full complement of electrons. That means the copper was reduced. Okay? So, another way you can think of this, and this is a way that helped me when I was learning, is if you think of a 0 and a positive and a negative. If you're becoming more positive, you're being oxidized. If you are becoming more negative, you're becoming reduced. Okay? More positive is oxidation, more negative is reduction. Now we can write these reactions as half reactions. Okay? The half just involving the zinc and the half just involving the copper. So the zinc half reaction would be the oxidation portion. Zinc goes to zinc ions plus 2 electrons. The reduction half reaction would be the copper gaining 2 electrons. So copper 2 plus the 2 electrons goes to copper. Now, if I were to add these two equations up, I'd have zinc plus Cu2 plus 2 electrons goes to zinc 2 plus 2 electrons plus Cu. Well, the 2 electrons are the same on both sides, so I can cross them off. And that leads me back to my original equation. Okay? So the sum of your half reactions has to equal your original equation. Okay? Otherwise, you have something completely wrong. All right, so there's some other confusing things that you should know about redox, and that is what we call oxidizing agents and reducing agents. Okay? So, a compound that gets oxidized can be said it causes reduction. So, whoever gets oxidized is called a reducing agent. So, zinc here, because it gets oxidized, It is the reducing agent. Reducing agent. So, the key here is, and the easy way to do this, is find out who gets oxidized, switch it and add the word agent. Oxidized, reducing agent. Okay? A compound that gets reduced is called an oxidizing agent. So in this case, the copper ions, because they got reduced, are my oxidizing agent. My ox agent. So why are we spending so much time on oxidizing and reduction, oxidation-reduction reactions? Well, they're a very important class of reactions, okay? As we talked about in the lab, many reactions, such as synthesis and decomposition, as well as all single replacement, are redox-style reactions. And redox-style reactions, because they involve the transfer of electrons, are going to govern a lot of important processes, like, metabolism, okay? Metabolism is all about the transfer of electrons because we use the electrons to actually create energy that our body uses. So, that's one aspect of it, but probably the one that you're most familiar with is the fact that iron rusts, okay? Protection from rusting things is a multi-billion-dollar industry. And it's quite fascinating. But rusting is a redox-style reaction. Iron combines with oxygen to form rust. So iron here goes from an iron that's neutral to an iron 3+. So this lost electrons, that means it was oxidized. Oxygen is reduced because it goes from a neutral atom to having 2 extra electrons, the oxide anion. So, let's put into place what we've already talked about too. Since iron is oxidized, we would call iron the reducing agent because it causes something else to be reduced. That means since oxygen is reduced, oxygen is the oxidizing agent. Hey, that's kind of funny that oxygen is an oxidizing agent. That's why we call it oxidizing agents, is because oxygen. Another example is batteries. The transfer of electrons is what causes electricity to flow. So in a typical alkaline battery, we have a zinc electrode and a manganese 4 oxide paste. The manganese gains electrons and gets reduced. The zinc loses electrons and gets oxidized. And it becomes zinc oxide and manganese 3 oxide. And the movement of those electrons is what causes the electricity to flow. It's the movement of electrons. So you can see if you were to actually cut open a battery, it would look much like this, where you have your zinc electrode, your manganese 4 oxide paste, and this brass pin is just used for the ability to connect out the electrodes. Now there's one other way that we can think of oxidation reduction, and this is useful for organic chemistry. Or, I said metabolism is a redox style process. How do I know? Well, oxidation results in the gain of oxygen. If you gain oxygen, you're oxidized. If you lose hydrogen, you're also oxidized. Okay, so this is kind of a funny one. If you gain oxygen or lose hydrogen, that's oxidation. Reduction would be losing oxygen atoms or gaining hydrogen atoms. That would be reduction. Okay, so let's focus on the oxidation portion. If I eat a candy bar, I use that for fuel. How do I get the fuel? Well, I have to do something really, really important, something that everybody does up until the time that they die, and that is breathe. Why do I breathe? Because I want to take in oxygen. The oxygen atoms actually react to oxidize molecules, which allows me to get energy out of glucose or sucrose in the candy bar. So it's about oxygen, the atoms gaining oxygen, or the molecules gaining oxygen, that is the oxidation. And it's the redox's role in metabolism is actually talked about in a video by Khan Academy, and I'm going to place the link here at the very end. So here's a link to that Khan Academy video. You don't have to watch this video, okay? I'm going to stall here so that you have time to write that down or put it into a browser if you wish. You don't have to watch it, but it is kind of neat. It goes over oxidation reduction, again, in terms of Gen Chem, and shows you how in biochemistry, or you can see this is an MCAT video, where it says MCAT in the browser here, MCAT. It's the same in medicine, okay? So all of this stuff that we talk about is directly relatable to medicine, to biology, to everyday existence, okay? So that's the end of this video. Now, there are plenty of other videos on stoichiometry that are posted online. I highly suggest you watch those, and to work as many problems as you can from the textbook, okay? And also, your lab book in the back has got a lot of stoichiometry problems as well. I would highly suggest you work those, and if you have any questions, please ask on Tuesday. So have a great rest of the week and a great 4th of July.